Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Now that we have covered quite a bit of physical metallurgy and thermodynamics and applying thermodynamics to materials, this is the right time to start on computational thermodynamics. We'll soon see the hands-on sessions with the softwares and all. Before that, we will introduce what is this computational thermodynamics and go forward. These are going to be the content of today's class: introduction to computational thermodynamics and some software tools used for this technique, and category of activities in this, and about the databases which are at the heart of all this. Basically, they contain Gibbs energy description, and we will see how the Gibbs energy descriptions look for unary systems, basically coming from SGTE. We'll see about that in today's class. Now, I welcome you to this computational thermodynamics. It originally started as CalFAD with capital C or all caps CalFAD. This is a kind of an acronym for calculation of phase diagrams. All these letters, first three here, and this D, they are taken to form this CalFAD term. There is a dedicated journal for this field, CalFAD, and the subtitle of the journal is Computer Coupling of Phase Diagrams and Thermochemistry. There is also a conference dedicated to this field, the 52nd version of this conference, International Conference on Computer Coupling and Phase Diagram and Thermochemistry, the CalFAD conference. The recent one was conducted in Korea. So this CalFAD is based on the science of thermodynamics. What it does is basically getting Gibbs energy descriptions of the system and using them for calculating phase diagram on certain material properties, especially the thermodynamic properties of materials. And here two things are in this yellow color: getting Gibbs energy and using the Gibbs energy, right? So that is at the heart of this technique. And of course, computers are used for these purposes. When we say computers, we're going to talk about some software tools. There are commercial and open source software tools available. For example, Thermocalc. In this course, we will be using Thermocalc to do some hands-on sessions. There is Pandat, there is FactSage, there is OpenCalFAD and PyCalFAD. These are open source softwares. These three are commercial ones. And there are few more. I didn't mention all of them here. Now, when it comes to category of activities in the computational thermodynamics, there are two broad categories one can say. One is using Gibbs energy descriptions, basically the Gibbs energy databases or thermodynamic databases, for calculating phase diagram and thermodynamic quantities and so on. This is called as thermodynamic calculation or simulation. Once you have the database, you can calculate phase diagrams and properties, and that is called as simulation. Okay, thermodynamic simulation or calculation. The other one is getting the Gibbs energy descriptions or making these databases itself. Perhaps this should be the first one, but there is a reason why I am putting this using as the first category. I will come to that. Now, this getting Gibbs energy descriptions is basically through a process called thermodynamic assessment or thermodynamic modeling or thermodynamic optimization. So this is where the modeling happens. So before coming to this course, you might be knowing that this course is on a modeling and simulation tool, and the modeling part is here, that is basically getting the Gibbs energy description, and simulation part is when once you make the Gibbs energy descriptions available in the form of databases, you use them to make the thermodynamic calculations. Once the thermodynamic assessment is done, Gibbs energy descriptions are ready, but they have to be put into a format called a database, thermodynamic database, a specific format which is readable by the softwares that we have talked about in the previous slide. So we need to have databases compiled in a certain format to be used with the software. These databases have Gibbs energy description of all or most relevant phases of alloy system of interest. So now we have talked about these two broad categories, and you see the common things. Gibbs energy description is here, Gibbs energy description is here, and database here, database here. So this database which contains this Gibbs energy description is at the heart of this entire technique. So we'll spend this class and the next class to understand what is this before going into the hands-on sessions. Later we will come to this thermodynamic assessment and all and see how the thermodynamic descriptions are basically created and so on. So this is the reason why I'm keeping this using Gibbs energy description as the first category of activities, because most users of CalFAD only do this part. They usually buy the commercially available multi-component databases and directly use them to make thermodynamic calculations or simulations. And this part, thermodynamic assessment or modeling, we can say it is dedicated to the CalFAD researchers. There are possibly few hundred people across the world who are able to do this at this point in time. Let's look at this Gibbs energy description in more detail. We will focus on unary systems and understand it. Think about this particular diagram. We have seen this in one of the previous classes. This is Gibbs energy versus temperature at 1 atmospheric pressure for aluminum. And there are two curves, one for FCC aluminum, one for liquid aluminum. You know what kind of information we can get out of this. There is a intersection here which says there is a melting point. Beyond that, liquid's Gibbs energy is lower than the solid's Gibbs energy. Therefore, liquid will be stable, and at lower temperatures, FCC is more stable than the liquid. There will be FCC being the stable phase, things like that. So there are a lot of information that this particular set of curves can give about the behavior of aluminum. Now, what we need to get these curves is the Gibbs energy description for each phase, right? For FCC and for liquid, we need equations for these curves. Okay, G as a function of temperature we need, that's what this is. But here pressure is taken as 1 atmospheric pressure. But if the pressure changes, these curves are going to change. Whereas Gibbs energy is also function of pressure, right? So what is Gibbs energy model now? Gibbs energy model is in essence the equation that expresses such functions, this kind of functions. G as a function of T and P, that's what Gibbs energy model is. So depending on the nature of contributions to Gibbs energy, different types of equations or models are used. Okay, what are these models or equations that we are talking about? They are basically the functions, Gibbs energy as function of temperature and pressure. And we are saying there are different contributions to Gibbs energy. What are these contributions? Let us look at them more carefully. Okay, think about this. This is Cp versus T diagram for iron with and without magnetic contribution. So we have seen this in one of the previous classes. So this dotted line is Cp of lattice and this solid line is Cp of lattice plus Cp physical, meaning Cp magnetic contribution. The magnetic contribution is called as physical here. So now these two things we have. So now two things contribute to Cp, right? One is the lattice vibrations and the other is the magnetic ordering. Both of them contribute to Cp, right? And if we have the Cp, there is a way to reach Gibbs energy from Cp, right? If you integrate Cp dt up to a particular temperature of our interest from a different temperature, we get the H value at that temperature, and entropy is Cp by T dt. Once you have the enthalpy and entropy, you can put them into this kind of an equation, G equals H minus Ts at the temperature of interest, you can get the Gibbs energy. So in this case, which Cp we start with? Is it this Cp lattice or Cp lattice Cp plus Cp physical? Depending on that, we are going to get different Gibbs energies, right? So Gibbs energy can be only G lattice, or it can be G lattice plus G physical, two separate contributions, depending on which Cp is used. So if we start with Cp lattice, we are going to get only G lattice. If we start with Cp lattice plus Cp physical, we are going to get the combination of both of them. Right. So in computational thermodynamics, it is useful to treat Gibbs energy of a pure element as a summation of various contributions. For example, the G of most elements, for example, aluminum, has only the chemical contribution or the lattice contribution. Okay, that is called G lattice. If there is any physical contribution, for example, magnetic contribution to Gibbs energy, for example, in the materials like iron, then it can be added as a separate terms. G physical can be separately added. Similarly, if there is a pressure dependency, if the pressure dependency of Gibbs energy is considered, then it can be added as another term, G pressure. Okay? So we need to have models, equations for each of them now. So this is how all of them can be combined, and G of a phase, G of a particular element in a particular structural state can be expressed. Now we have this SGTE which gives the unary descriptions. It's called Scientific Group Thermodata Europe. It's a consortium engaged in the development of thermodynamic databases. So this consortium has come up with this G lattice of an element in structural state I. I can be a few different structural states. Okay, let's say BCC, FCC, liquid, HCP, like common structures. Okay, so G of lattice in these different structural states for an element as a function of temperature is given by SGTE, and it comes usually in this format: G of an element I in a particular structural state is equal to A plus BT plus CT LNT plus summation of DT power n. The summation is over n. In the next slide we will see in more detail what is this equation. So we will have numbers for this A, B, C and all. So this is the model for unary Gibbs energy in SGTE, and this A, B, C are called model parameters. So now once we have the Gibbs energy, can we get the other unary state properties from that? It's possible. G lattice of an element in a structural state I is expressed by this particular model called Mayer-Kelly polynomial. It looks like this, where this A plus BT CT LNT is there, plus summation of n can be 2, 3, minus 1 and so on, dn t power n. So this is how complex the equation can get depending on what is the element and structural state we are talking about. And if we have this G expressed like this, G equals H minus Ts, then from this we can get this, right? If we differentiate G with respect to temperature, then here there is no T term, this is going to be 0, there is a T term here, you get only S here. So therefore S is going to be equal to minus dG by dt. Assuming that this H is independent of temperature, we can do this. Now if we have S as minus dG over dt, then we can differentiate this entire equation and put a minus symbol in front of the terms. Then we get this expression. Now we got entropy from Gibbs energy. The meaning here is G is available in the SGTE databases. From that we can get S. And we can also get H. You can see here, if we keep the H on the right side and take Ts to the other side, it's going to become positive. Then if we can take this G and take this S, multiply this with the T and add it to G like this, G plus Ts. So we can get the expression for H. And once we have the H, dH by dt, at constant pressure, we are writing Cp, right? At constant pressure, dH is equal to del Q, you remember. So the amount of heat required for a temperature rise, that is Cp, and we can differentiate H with respect to T and get Cp. So this is how we can get other thermodynamic quantities from Gibbs energy. Right. Now what is the reference state here? We have to write GHSCR, Gibbs energy with respect to a reference state. Okay. S has an absolute value, we know that at any temperature, but H or G has no absolute value. Therefore we need to have a reference state. We can keep H298 as the reference state. Okay. In that case, G minus H298 is what we are going to use. We are going to call it GHSCR. SCR stands for Standard Elemental Reference, and this is what it is. Now what about pressure and temperature? Pressure is kept as 1 into 10 power 5 pascals, atmospheric pressure expressed in pascals. Currently the expressions are made for above 298 Kelvin, meaning from 298 till higher temperatures as high as 6000 Kelvin and all, we have the expression for various elements, but not below 298. Multiple expressions are used for a single element in a single structural state, each one corresponding to a range of temperature. So we'll see what is this in the next slide, meaning what is the pressure used for the SGT expression and temperature used for the SGT expressions. That's what is given in this slide. So this is the actual expression for silver from the SGTE database. This is a screenshot from the PDF file itself. This is for FCC A1, and I don't think you need to feel intimidated about the complexity of this equation. This is the reason why we have been developing all these ideas one by one. So this is what the Mayer-Kelly polynomial looks like, A plus BT plus CTLNT and so on. So that is what you are seeing here, and this entire thing is true for a temperature range from 298 till 1234. This is the temperature range over which this first expression is valid, and from this temperature onwards till 3000 we have the second expression. Similarly, for liquid we have two different expressions for two different temperature ranges. SGTE also gives data with respect to the standard state, that is FCC-A1 for silver at 298. So based on that, the liquids expressions are given here. You see, the first term you can try to compare here, minus 7209 here for FCC. Here it is plus 3815, right? So the difference between them is here 11,000. Meaning if you add this first term 11,000 something to the 7,200 value, you will get this 3,800 value, right? So it means expressing another phase Gibbs energy data relative to FCC A1, meaning this value is assumed to be 0. If this is assumed to be 0, then from here this data is about 11,000 away, right? So if this 7,200 is going to become 0, then this 3,800 is going to become 11,000, right? So it's basically moving the scale. That's what data relative to FCC A1 means. So this also comes in the same database. But how this actually looks in a database file? This is a PDF file I said from SGT. The data is published in that PDF file. From there, we can put it into a TDB file, and this is how the TDB file looks. TDB stands for thermodynamic database. That is an extension used for the database files, and this is a screenshot of a small part of a TDB file. Okay, so here you can see FCC A1 written in SGTE, and this is how the expression is given, and the same thing is written in a TDB file in this manner. Okay, function GHSCR AG, Gibbs energy with respect to HSCR, standard elemental reference enthalpy, for element silver Ag, and the lowest temperature is there here 298.15. This data comes here, and then the expression starts. Okay, this entire expression starts from here. So there is a particular format in which it is written, and after this semicolon, the upper temperature limit 1234, that is also written here. Okay, so from this temperature 298 to this 1234, this expression is valid. That's the meaning of it. And then the second expression is also given after that. Okay, this is how the TDB file is written, and this is G liquid Ag. The liquid Gibbs energy of silver is given here. Again, between a temperature range, what is the expression? Since this 11,000, this value is used here, of course this is with respect to FCC A1, right? FCC A1 data is written as GHSCR. Silver in its standard elemental reference is in FCC structure. Therefore, whatever is the FCC value written here, in fact here it is not mentioned as GFCC of silver. It is mentioned as GHSCR of silver. This is the standard state, FCC state of silver. In the database that is defined in the beginning itself, but here this is the meaning of it, I am telling you directly. Now GHSCR, we have to put it here and then add this 11,000 to that. Okay, that is how G liquid is expressed in this database file. You don't need to feel that this is too complex or you need to memorize or something. This is basically for you to understand what is a Gibbs energy model, description and database. About each of them we will see in detail in future. But before starting the hands-on sessions, it's good to know what is this database and what does it contain, what are the Gibbs energy descriptions, how do they look, so that you have a feel for what happens inside the software when we use the database. right? Now this is a G physical and G pressure. This is the SGTE data for pure element iron. For iron, apart from this temperature dependent term, the lattice term, we have G press plus G mag. Okay, pressure Gibbs energy and magnetic Gibbs energy. Two terms are added here. In order to calculate these two terms, we need more information. That information is given here. Tc, B naught, A, small a naught, A1, K naught, K1, N, and so on, right? So these are all important to calculate these two terms. Let's look at those two terms in a little more detail. For G pressure, we cannot use Mayer-Kelly polynomial. That is not suitable. Another model is Murnaghan model. This is the expression for that. So you can see the pressure term P comes here, and there are other this A0, A1 and all material constants. Different kind of values are given here, and these are all the values given in the previous slide for iron. So in essence, what I'm trying to say is the pressure dependency of Gibbs energy can be modeled in a different way, and it can be added to the Mayer-Kelly polynomial, which is basically the lattice contribution or chemical contribution to Gibbs energy. So this is the magnetic transformation part. We have talked about it. We have talked about it some time ago. Here also Mayer-Kelly polynomial is not suitable, and Inden-Hillard-Joule model is used, and this is the magnetic ordering Gibbs energy, GMO. This is the G physical now. RT, natural log of beta plus 1, and G of tau. G of tau is a function of tau. This beta is magnetic moment, and the tau is temperature of interest, where we are calculating G divided by Tc. This Tc is critical temperature for the magnetic transition. Basically in para to ferro, we talk about a Tc being Curie temperature. In antiferromagnetic materials, we talk about Néel temperature. These are the critical temperatures for magnetic transition, and they are used in this G term. Now this G of tau is written. G of tau is again a complex function. This is the expression for that, and here also we have this P, D and all. This D is again calculated based on P. This is a material constant. I am not giving all the details of that. Basically the magnetic contribution to Gibbs energy is modeled differently in this manner, and it is added to the Gibbs energy description. Right. So this is in a way a summary of what we have seen till now. SGTE provides pure element Gibbs energy data in various structural states with reference to HSCR and GHSCR. Various contribution to Gibbs energies exist. For each, there are separate suitable models are used. For example, for lattice or chemical contribution, we have Mayer-Kelly polynomial, and for pressure contribution, we have Murnaghan equation, and for magnetic ordering, we have Inden-Hillard-Joule model. In the next class, we will see about the binary contributions to Gibbs energy. Thank you. I hope the lecture is useful. See you in the next class.